Okay, so we're going to look at a very interesting example. Well, I shouldn't say very interesting example. It's much more interesting than the examples that we've looked at so far. So in the examples that we've looked at so far, the PDE, the solution, has been constant along characteristic curves. We're going to look at an example of what happens when the solution is not constant along the characteristic curves. Okay. And so this is what we have here. Again, this is our general setup. I want to find the general solution to this. So one of the things that I mean when I say this is we're going to have to figure out where we want our Cauchy data to be. So we're going to kind of make generic Cauchy data. The method of level sets is kind of difficult here because the PDE is not going to be constant along. So the reason we could use the level set method in previous examples was because the PDE was constant along the characteristic curves. It's not constant along the characteristic curves, and we'll talk a little bit why in this problem. So I'm just going to add this condition, a Cauchy condition. I'm going to just add the condition. I'll make things a little bit different. I'm going to say u of 0 y is equal to some known function, some given function, f of y. Okay, so instead of knowing it along the x-axis, we know it along the y-axis. Let me kind of draw my coordinate system here again so we can all laugh at how bad I'm able to do this. But the x-axis doesn't matter so much this time, so I'm just going to have it like that. Okay, so now my characteristic equations, what are they? X dot is going to be the thing multiplying the partial derivative with respect to x, so that's going to be 2. X of 0, well, if I'm going along the y-axis here, if my Cauchy data is the y-axis, x of 0 is going to be equal to 0. Y dot is going to be equal to 3, and that's just going to be a generic point on the y-axis. Why not? Okay, but now look at what's happening with z of s. Again, this part right here is always going to be z dot. So this says z dot is equal to minus u. But remember, along the curve, u is equal to z. So this tells us z dot is equal to minus u, but along the curve, z is equal to u. So in other words, z dot of s is equal to minus z of s. And z of 0, again, is just going to be equal to u of x of 0, again, because z of s. Actually, it might even be helpful to do this calculation here, just so you guys can kind of see what's going on here. So I want to show that z dot is equal to minus c. So let me do that now. So remember, z of s is always, when we do the method of characteristics, we always have the following. So this is always true for the method of characteristics. Z of s is equal to u of x of s, y of s. And so again, by using the chain rule, I'm going to get z dot of s is going to be x dot of s times the partial derivative of u with respect to x plus y dot of s times the partial derivative of u with respect to y. Okay, so what is x dot of s? X dot of s is equal to 2, so this is 2 times the partial derivative of u with respect to x. And again, I haven't been so clear here, but we're evaluating this at the point x of s, y of s, and then y dot is equal to 3. So this is going to be plus 3 times the partial derivative of u evaluated at x of s, y of s. Okay, but what does the PDE tell us? Well, this 2 partial xu plus 3 partial yu, that's this part here, and that's equal to minus u. So this is equal to minus u of x of s, y of s. And this is just equal to minus z of s, which is what we got up here. I'm going to try to write this a little more clearly. So z of s is equal to minus z of s. And then still, z of 0 is going to be u x naught, y naught. So this is just going to be f of y naught. Okay. So I'm going to erase all of this. Okay. And again, I want to highlight the purple line here. I want to highlight the Cauchy data here. So this is the Cauchy curve here. Okay. And again, I can very easily solve for my x and y characteristic curves. So for my x curve, x of s is going to be equal to 2s. Y of s is going to be equal to 3s plus y naught. Okay, so now y naught is going to be the y-intercept, and it's going to, the characteristic curves are going to be lines that go through the purple part at y naught, and the slope is going to be 3/2. The 3 divided by 2, that's the slope. Okay, so again, the whole point, the whole deal with the method of characteristics, I'm going to pick some point. I'm just going to pick some generic point, A, B in the plane to analyze. I want to trace the characteristic curve back to the purple line here, back to the Cauchy data. So the characteristic curve is going to go through here and going to have a slope of 3/2. So 1, 2, 1, 2, 3, 1, 2, something like this. Okay, and now I just want to look along this one characteristic, and let me think about what's going to happen. So if I just look along this curve here, the solution along this curve here is equal to z of s. Z dot of s is equal to minus z of s. So this tells me that z of s is going to be equal. So you need to know the solution is going to be equal to z of 0 times e to the minus s. What is z of 0? Z of 0 is f of y naught. So this is f of y naught times e to the minus s. So what this is saying, if I look at my solution along this curve here, at this point right here, it's going to be this corresponds to s is equal to 0. So along this curve, my solution is equal to f of y naught e to the minus s. So if I go s units along this curve here, my solution is going to be f of y naught e to the minus s. Okay, and so the idea is I've sort of have solved the PDE along this characteristic curve here. The idea is I want to somehow piece that together to get the solution for the whole plane. And the way that I do that is the following. I know that u of AB, again, for my generic point here, u of AB is going to be equal to f of y naught e to the minus s, but I need to figure out how I write y naught and s in terms of a and b, and that'll tell me what u of AB is. Okay, well, I'm going to do this very similar to how I've solved the other equations. It'll be just maybe slightly more complicated now because notice, unlike in the previous examples, I only needed to know what the x naught or the y naught is because the solution is constant. But for this one, for this problem, I actually need to know what the s is as well. So A is equal to 2s and B is equal to 3s plus y naught. Well, this equation here tells me that s is equal to a over 2. So s is equal to a over 2. So this is going to be 3/2 a plus y naught. So then y naught is equal to b minus 3/2 a. So u of AB is equal to f of y naught in terms of a and b. Y naught is b, b minus 3/2 a, and then e to the minus s is going to be e to the minus a over 2. Or again, I'm using a and b because I'm already using x and y here. So if I want to switch back to x and y, which is how we really think about the points in the xy plane, u of xy is equal to f of y minus 3/2 x times e to the minus x over 2. So that's my solution. Since this was kind of a little more complicated, I want to actually show that this satisfies the PDE. Now I need to figure out how to add a page again. Where is it? Insert new page, insert after. Okay, so u of xy, u of xy is equal to f of y minus 3/2 x e to the minus, let me just make sure, y minus 3/2 x e to the minus x over 2. Okay, so now I'm going to do 2, what was the PDE? Yeah, 2 times the partial derivative of u with respect to x. So if I do 2 times the partial derivative of f with respect to x. Notice for the x derivative, I have to do the product rule. So the derivative of f with respect to x using the chain rule is minus 3/2 f prime of y minus 3/2 x e to the minus x over 2. And then now I need to do plus f of y minus 3/2 x times the derivative of this. Let me just go ahead and turn this into a, whoops. So this is minus 1/2 e to the minus x over 2, and then plus 3 times the partial derivative with respect to y. This is a little simpler. As the derivative of the inside with respect to y, which is 1, times f prime of y minus 3/2 x, and then as far as x is as far as y is concerned, e to the minus x over 2 is equal to a constant. Okay, so let's see what's going to happen here. When I distribute the 2 and the 2 there and the 2 there cancel. So I've got minus 3 f prime e to the minus x over 2, and that's going to cancel with this right here. And this is going to give me 2. So this term, so what I'm saying is this term and this term will cancel, and that's equal to 0. And then I'm just going to be left with this term here. But when I multiply it by 2, the 2 there and the 2 there cancel, and this is minus f of y minus 3/2 e to the minus x over 2. But notice this is just equal to minus u of xy. So on the left-hand side, I've got 2 times the partial derivative of u with respect to y plus 3 times the partial derivative, or sorry, I've got 2 times the partial derivative of u with respect to x plus 3 times the partial derivative of u with respect to y, and it's equal to minus u, which is exactly what the PDE says. And then if I look at u, to make sure it satisfies the Cauchy stuff, if I look at u of 0y, if I look at u of 0y, I get f of y minus 3/2. Well, if x is 0, this is just f of y, e to the minus 0 over 2. Well, that's just equal to 1. So this is f of y. So this satisfies the Cauchy problem. The Cauchy problem, meaning the PDE and the Cauchy condition, the Cauchy data, the condition that it satisfies the values of u along the curve. So this satisfies the problem. Okay, that was it. So again, very new, new thing going on in this problem where we're actually the solution is not constant along the characteristics, a little more interesting, but again, very similar pattern to how we've seen the more simple problems.